Hello, my name is Ted Zoli. I'm here to present on rapid fabrication of resilient steel bridges and our ideas about built-up press brake form tub girders. My colleagues in this are Dr. Ashley Thrall at University of Notre Dame, our Indianapolis office at HNTB, including Tom Bieneman, Stephanie Wagner and Prince Ba, our Indiana DOTs. They're the project sponsors, as well as Vin Bartuka from National Steel Bridge Alliance and Mark Haight from Inframetals. When we think about accelerated bridge construction, and this is a project we were involved in developing the Sharp 2 toolkit for accelerated bridge, a hallmark of accelerated bridge construction is doing a whole lot of work without interrupting traffic and then over a long weekend replacing bridges. This is a corridor in I-84 in New York where we replaced two mainline bridges over a weekend. But what you don't hear about is the 10 or so months of construction it took to get ready to prepare for this weekend outage. And so we got very interested in Dr. Thrall's kinetic structures lab, got very interested in could we dramatically shorten the time it takes to fabricate components. And so this research is all about maybe not accelerated bridge construction, but accelerated bridge fabrication. And our goal here is to take fabrication, particularly of steel girders, and instead of that taking tens of weeks or months, trying to reduce that into a matter of a few days. And obviously, because we're interested in streamlining not only the fabrication process, but also design and shop drawings, we're using a kit of parts approach. And in terms of motivation, a lot of what we see, and if we spend some time just talking about climate change and its impact to bridges, there are significant bridges in the Northeast and Midwest part of the United States that are affected from enhanced inland flooding associated with extreme precipitation events. And the numbers are really troublesome. We see anywhere in the neighborhood of 40 to 50% increases in the last 50 years of the 1% or 2% rain events. And inland flooding has become a real problem, not just in places like Indiana where our research is being conducted, but really all throughout the Northeast. And when we think about just what happened during Hurricane Irene, now Vermont doesn't have any coastline and we don't think about hurricanes, and really Irene turned into a tropical storm by the time it reached Vermont, but we had significant rainfall events and an incredible amount of damage to bridges. So flood damage included almost 200 bridges on the state highway system and nearly another 300 bridges on the municipal system. And one of the roadway reconstruction, that was pretty rapidly restored, but bridges take much longer. And in the lower right-hand corner, this particular bridge wasn't completed till 4.5 years after the event. So in 2016, and you see the challenge that we have many relatively modest span bridges that take us forever to replace, and can we dramatically enhance our ability to replace these bridges rapidly? So in terms of the research program that we have outlined, and we're roughly halfway through that, we have really, it's broken into two parts. One is to both investigate the behavior of demonstration bridges that we both design and deploy, and the other part is to develop this design and strategy and kit of parts and a catalog for bridges so that bolted up tub girder bridges could be used literally anywhere. So this is a joint project. So HNTB is the engineer of record for these tub girder bridges, the two projects we've selected, and then working together with Dr. Thrall's and her grad students from Notre Dame, we're developing this kit of parts, and also there's quite a bit of field work to verify and validate our design methodologies. So we owe a lot to past researchers and in their work on using press brake strategies for tub girder projects. So there's really two areas of work. both of which are robust, and so there's been many deployments of these types of systems. So there's a press brake form tub girder, which is more like what you would expect, a trapezoidal shape with a deck on top. And then there's a folded plate, steel plate girder tub system, which actually is an open section, but it's if you will, an upside down U. And both of these systems have been deployed and are quite effective strategies for bridges with spans on or less than 60 feet, given the limitations. That's typically what the maximum length of a brake press, and they're all fabricated out of mill plate. So the maximum width of mill plate is typically 120 inches. So this implies span length limitations and also plate thickness limitations. So most of these bridges have plate limitations on the order of a ½ inch or 5/8 of an inch thick. And so we're very interested in, although that's an important span range, and there's many bridges in that span range, we're interested in what's more typical of conventional plate girder span ranges, so well north of 100 feet or more. So our built-up tub girder concept uses only press brake bent webs, and the flanges, both top and bottom flanges, are bolted. Our strategy here is to engage with transmission pole fabricators, and this stemmed from a conversation that I had with Inframetal's president Mark Haight at a NSBA conference about looking at what their skill sets were and how we could map them to the bridge problem. By press braking the webs only, now that 120 inches can turn into quite deep girders, so we can have girder depths on the order of 8 feet and span lengths that are approaching 300 feet. We're still limited by the press brake lengths of 40 or 60 feet, but that's a reasonable transportable segment, and we can assemble these components into longer spans if we want to erect 80-foot or 120-foot segments. There's no problem with we're simply bolting these segments together before we erect them. So nothing unusual, the typical sorts of erection, but this strategy keeps everything very readily transportable. Obviously in the upper right you see a corded arrangement with the press brake. We're making everything straight, piecewise straight, and making up the angle brakes for curvature at the connections, and we've done quite a bit of research on that in the past. And so we also are only changing cross-section between splices. So this 40 or 60 foot length becomes a very useful way to think about where your section size changes. So this is the strategy. We're also taking some deep advantage of research by others, particularly in terms of redundancy. So Purdue has done a really fantastic job at establishing how built-up sections are internally redundant. They had quite a time demonstrating even the failure mechanisms with modern steel. So this is a research program where looking at bolted cover-plated girders, so you see a clip angle and that bottom flange plate with a through crack, and trying to assess whether that crack would propagate into any of the adjacent components, whether it's the web or the clip angles. And they tried like hell, including cooling the entire assembly to -83 degrees to make sure they're on the lower shelf of fracture toughness. Driving wedges, you can see the driving wedges just to force the crack to propagate across the cross-section. And in no circumstances did they have that crack propagate into any component. And this really just highlights how effective internal redundancy is as a strategy. And you get the idea. What we did in the riveted girder days probably has a big advantage in terms of overall safety and internal redundancy. And so we're taking advantage of that internal redundancy in the design of the press brake tub girders. In addition, Eric Williamson at UT Austin with grad students has also done a significant amount of work on looking at the redundancy, system redundancy of twin tub girder bridges, and this is another one of just trying everything you could to get these systems to fail. So not only was the bottom flange cut explosively, and it did very little, I think it was 1-inch deflection, he then cut the webs and then supported the span with simulated live load above it, and then explosively cut the supports to try to get fracture to propagate. And even then, he got very little deflection, I think 7 inches, but fully capable of supporting live load. And it was only, it took statically adding 5 times the legal load limit of 363 kips on the bridge to get it to fail. So this just shows you that tub girders are incredibly, even twin girder systems, which we might consider as fracture critical, are incredibly capable of load redistribution and redundant behavior. So tub girders for us are really a natural choice to get very both cost-effective and safe and redundant structural systems. As I mentioned, we've done work in bolted plate connections and bend plate connections. So this was work also done under Dr. Thrall and looking at bolted connections with angle breaks, and you get the idea with corded sections, whether vertically corded to get profile or corded in plan to get curved girder behavior. Bend plate connections are an important consideration. This work by Evan Gerba really demonstrated how effective these connections can be and looked in great detail at the behavior of the bend plates themselves. And bend plates are obviously an issue here with using bend plate webs as well as bend plate connections. So I'll spend a little time talking about plate bending. So this is typical press brake bending work, and so we've done quite a bit to assess what is happening with the steel just from flat plate to bend plate. And in this research, we used digital image correlation. So by etching the plate with a pattern, we were able to with digital image correlation, which is essentially stereoscopic, two cameras, which then collect 2 images, and those 2 images are put back together to get 3-dimensional behavior. And by patterning each plate, we can accurately calculate the differences between points and then back calculate strains. And so you're seeing here on the left the comparison of digital image correlation of an actual bend plate as compared to a finite element simulation. And obviously we're looking here at plastic strains. We started this program thinking we could use strain gauges, but strain gauges and their ability to survive the press brake was a concern, and we really validated the value of digital image correlation to understand behavior of bend plates. And so this is a close-up of what that image looks like, and the patterning becomes important. So we're either using ellipses that are randomly generated or using squiggles, and we've used this on other projects to be quite effective. So these patterns, because they're randomized, the software can tell relative, at the pixel level, relative displacement from one pixel to the next. So this is an image of the strain profiles as overlaid on the actual bend plate. And you can see here fairly significant plastic strains, which are well predicted by equations. And even we've accounted for a neutral axis shift and have a pretty good understanding of the way plate bending works with press brakes and what that does in terms of introducing strains into the steels. We've also taken that digital image correlation on the road and have developed patterning for stickers and applied stickers to painted steel bridges, and have demonstrated that it's quite an effective technique in the field. And so we've looked at, on the upper left is a truss bridge that had a cord fracture that we used digital image correlation. The right hand one is a cable stay bridge where we can not only see stress profiles but calculate principal strains. So we're getting a sort of a finite element overlay, if you will, of strains over quite a complex system. This is near the tie down of an end floor beam of a cable stay bridge. And then quite a comprehensive bit of work done for Indiana DOT on the behavior of impacted girders. So this is looking at load shedding when an outside girder has been impacted and you get flange deformation and you've now loaded it with trucks. Where does the load go? Does it go to the interior girders? How much stays in the fascia girder, and does the fascia girder need to be repaired? All of that technology of using digital image correlation we're planning to use on our deployed bridges to measure not just behavior under live load, but we can measure behavior under dead load. So we will pattern and take photographs of the bridges prior to their being erected, and so we'll get what I think will be for the first time both dead load and live load behavior. Now a bit about those two bridges that are our demonstration projects. One is replacing a 3-span continuous bridge with a 2-span continuous. So we want to demonstrate with our technology that we can do continuous systems, and the longest span here is over 100 feet, 105 foot, and 86 feet. And for a simple span bridge, which has, I think the original bridge has about a 72-foot span, we're extending that to 97 feet just to get better hydraulic opening and better abutment behavior. But that's a simple span bridge at nearly 100 feet. So to do a little bit of a comparison of before and after, the conceptual design for the bridge was pre-stressed girders. This is a 5-girder system for the simple span, and we're replacing that. Our alternative with tub girders is to use it's a 4-girder cross section, and the girder depths are roughly the same here. And so these are quite shallow depth tub girders, and we're using basically 1-inch steel flanges and 5/8 steel press brake bent webs. For the 3-span continuous, the big advantage of going to tub girders is that we can actually reduce the number of spans, so that the preliminary design for this was still a 3-span bridge with pre-stressed girders, and our approach is to actually eliminate one of the substructures and reorient so that we have a 2-span continuous, and we go to tub girders, and now we have eliminated a substructure unit, which is a big advantage because this is also one that's subject to debris accumulation. So we've got better hydraulic opening, less construction costs associated with substructures, and easier erection. So our proposed substructure also is just the extended drilled shafts with shear walls supporting each tub. This is also staged construction, as of course many projects are. So the construction staging very quickly is to build and shift traffic one lane at a time to the new bridge built in halves. And so we also want to demonstrate that this technology works in staged construction. And obviously, because these are infill arches, the demolition, we've left 3 foot clear just to make sure that demolition of the existing bridge doesn't get fouled by the new bridge. And so we've got a work zone for complete demolition, and then the second phase, so this will be phase construction, is connecting the identical span with a longitudinal joint. So we'll also, in terms of this evaluation, be able to look at load distribution and redistribution through stage construction, which will be quite useful. The big takeaway here is not just the savings of a pier, but the significant savings associated with lifting and lifting activities. So the tub girder is roughly half the weight of a similar pre-stressed girder for similar span lengths. So there's a big advantage both by pier elimination. We've significantly reduced not just the weight of the picks. So we've gone from a 36-ton pick with a 3-span continuous at a 100-foot radius to a less than 30-ton pick at a 50-foot radius. So significant reductions in crane activities, and the cranes placed behind the abutment here, as well as a third reduction in the number of picks. So we see big advantages to transport and erection associated with going to tub girders, and pier elimination is obviously an advantage. So as part of the research, in this kit of parts ideas, we've developed parameterized models all within Abacus. So every one of these parameters is something we can change with respect to each individual girder and also girder spacing, deck thickness, and so on. So the idea is to have a fully parameterized set of FEM models, and so then we can do parameter optimization for this development of a kit of parts. And so I want to spend just a moment or two talking about, obviously in press brake bent systems, we're using a press brake to bend steel, and that whole question about what steel should we use and what does bending do to steel. So this will be a little bit of an aside. Part of our motivation was to use workflows that are associated with transmission pole manufacturing. And the more we got into this, and with the help of Mark Hayden at Inframetals and some of his staff, we got a better understanding of what steels they use and why they use them, and how they might be a deep advantage for using those steels for our tub girder project. In particular, they're typically using 65 KSI steels, and the ASTM A572 at grade 65, which is a bridge steel, they also use that's a steel that they would typically galvanize. And ASTM 871 is a pole steel that is typically a weathering grade. So there's both weathering grade and normal grade steels that we would be familiar with. But what's fascinating is that their CVNs are specified, similar CVNs, the 15 foot-pounds, we would typically specify 15 foot-pounds at 40 degrees Fahrenheit. They're specifying at minus 20 degrees Fahrenheit. And it turns out that specifying a minimum Sharpies at a much lower temperature is really the right strategy when you're looking at cold working. Most of the press brake bent tub girders have been using AASHTO steels, so A709 grade 50 steels, and bending to AASHTO limitations, which is typically a 5T bend radius. Whereas in poles, they're bending to a tighter radius, and our goal is to use conventional press brake manufacturing around poles, so that we wanted to use both pole steels and pole dies. So we don't want to change out the dies. We want someone like Inframetals to be able to make us a web without changing his production capabilities, or not retooling in terms of dies or anything else. And here you can see this is a press brake of a tapered section, a tapered pole, and tapered sections in tub girders is also possible for obviously using the same strategies. So at any rate, if we talk a little bit about why temperature shift is the right strategy, if we go back to why we use CVNs or Sharpie V-notch to get an assessment of toughness, and what our goal here is to make sure that in the operating temperature that we're using the steels, that we have adequate toughness against crack propagation. And so typically we're testing at lower temperatures, and we're using as a design basis the temperature, the in-service temperature, the lowest in-service temperature. So, for these projects in Indiana and for the Northeast, we're typically talking about Zone 2 Sharpie requirements. And there's this temperature shift not only applies to cold working, as you see in the right-hand graph, but also it applies to the toughness of steels depending on loading rate. So this idea of having, let's say, lower temperature toughness inoculates you against some cold working and also some dynamic force, because the Sharpie V-notch is a dynamic, more or less a dynamic test, and typical bridge behavior is more in terms of strain rates is in the intermediate range, maybe even closer to static. So this 40 foot-pound, the 15 foot-pounds at 40 degrees Fahrenheit has associated with that taking advantage of the fact that we're testing dynamically, and we're actually using the bridge uses more intermediate strain rates or statically. But when we're talking about cold forming, we're very interested in making sure that we have a margin, because what happens when we cold form, when we cold work the metal, we get a reduction in toughness, and that can be well thought of as a temperature shift. So one of the arguments that, and this is maybe even applies to AASHTO, when we cold work steels, we really should be starting with steels that have higher toughness, and not just higher toughness at the let's say an operating temperature, but it's better to have higher toughness at lower temperatures because of this temperature. So we've learned a lot about this sort of behavior from roll form structures like steel tubes. So HSS, whether rectangular or square tubes, have this problem of a bend radius in the corner, and then typically a weld at. So these are typically formed by roll forming, and here you see the same temperature shift. This is in the Eurocode uses a temperature shift as an approach to evaluating the toughness of cold worked. And they don't specify cold working, but cold worked steel. And here these are CVNs of, you can say the flat is not cold worked on a rectangular or a square section. The corner is cold worked, and the black and the red are the difference between the two. So I'm using the same philosophy. We want to start with better toughness so that when we take a temperature shift into account, we end up with better toughness or with adequate toughness of the finished product. In the Eurocode, they use this degree of cold forming, which is associated with plastic strain, but slightly modified. And you can see a great correlation with the degree of cold forming. So no cold forming, you start with really good toughness, and as you cold form and you strain the steel more plastically, you get reductions in toughness. And the idea here is lower strain, less reduction in toughness. So bigger bend radiuses are helpful. But you could also get at the success by starting with better toughness material in the beginning. That's where I want to head to next. So it turns out also that the lower the carbon content and the higher the manganese content tends to head you in a place where you start with better toughness at colder temperatures. And so the steels developed for the transmission pole business have just that, tend to have lower carbon and higher manganese contents. And this is a typical example when we asked Inframetals for a typical example of 5/8 inch plate that we're going to use for our projects. This is what we see. We see CVNs of an average of 100, so 15 would be the minimum at minus 20 degrees Fahrenheit. And if we go through and compare pole steel and this 5T temperature shift, which is permitted by AASHTO, and we compare what we're getting, even meeting the minimums, we find that bending to a tighter radius, this 3.5T, which is typically used in transmission pole fabrication, we're very comfortable. We can meet the AASHTO requirements assuming no cold working. So our approach here is to use, rather than using what I would say are A709 grade 50 materials, to use transmission pole manufacturing materials which are on hand as the basis for and bending them to dies that are typically used in transmission pole fabrication to make sure that we meet our minimum toughness requirements. And we think that this is the right strategy. We're really trying to adapt workflows from transmission pole manufacturers to get new fabricators into the market. And so these are the ASTM 871, which is not a steel we use in bridges, has exactly this 15 foot-pounds at minus 20. And it's interesting, when they use 572, grade 65, which is a steel that doesn't have an ASTM, in the ASTM doesn't have a minimum CVN. When they use it for poles, they specify the same absorbed energy. So that's exactly the strategy we have, is to specify minus 20, 15 foot-pounds at minus 20 as the grade of steel or the characteristics of steel we need for our press brake webs. Now a bit about the modeling. As I mentioned, we have everything parameterized. This is some details of the simple span, the 97-foot simple span bridge model. In Abacus, we have pretty well everything modeled in quite a bit of detail: lateral bracing as angles, connections, end diaphragms, intermediate diaphragms with the openings, even openings in the bottom flange for construction access. Much more sophisticated than what we would do in the design, in a typical design office, where in this case we're using CSI Bridge and their tub girder wizard, which we found quite good correlation. So the Abacus models gives us much more detailed assessment of some of the components, but we want to make sure that a typical design office workflow can handle the design of press brake tub girders. Also, we're using Indiana DOT's semi-integral end bent conditions, so we've adapted some of our details to use to avoid joints and use conventional semi-integral abutment type connections that are common in Indiana. As part of that, this system, we're actually using there's no welds on anything other than the shear stud welding at the end. We're using all bolted up clip angle connections and diaphragms. We're using rolled sections as well as using rolled sections for the intermediate diaphragms. And we're coping the web so because typical transmission pole manufacturers have sophisticated burn tables, we can drill the holes for the connections as well as cope flanges or cope webs prior to bending. So all of this would be done on a flat burn table prior to bending, and then the bent product would come out ready for installation. As I mentioned, internal diaphragms are an important consideration. So we've both got a rolled section, a full depth or nearly full depth diaphragm, but we're also, in order to provide a continuous access to the inside of the tub girder, we're using diaphragms with significant cutouts. And those diaphragms are an important consideration, and because we're roughly a little bit more than 36 inches deep, we spent a lot of time looking at, and we're not expecting, because these are internally redundant and system redundant members, the need for inside inspection, but we didn't want to preclude inside the box inspection. So we did quite a bit of work on diaphragms and diaphragm sizes. So just in terms of diaphragm opening requirements, most states have standards that are not necessarily easy to meet given shallow depth girders like we're looking at for these demonstration projects. And both AASHTO and OSHA don't have explicit requirements for bridge inspection. But what we did find was some documentation both in the building code, both IBC and IRC, for minimum requirements for emergency egress. And those are 24 inches minimum height, 20 inches minimum width, and this cross-sectional area, which makes a lot of sense, of 5.7 square feet. So all of the openings that we've developed for our tub girder projects have meet these IBC and IRC emergency egress and rescue requirements. So we're also explicitly modeling the openings and the opening geometry just to make sure stress state that we don't have any issues. This is dead plus live, so we're really not working any of this steels very, so these are, just to give you context, 5/8 inch webs, 1 inch plates. The top flange are 18 inches wide, the bottom flange is 34 inches wide. We're at service load levels for 50 KSI steel, and remember the webs are 65 KSI steel. We're working at 17 KSI, so we have plenty of residual capacity. If we separate the elements, we see that we don't see the bend in the girder web producing any localized stresses. The stresses, the girder web, we'll call it the bottom flange section, follows the bottom flange, the top flange the same. We obviously, in this case, have a higher strength, higher yield strength web than flanges, not intentionally, but because we can. So if you think about it in that context, that we're really not working the webs very hard at all. Also, these FEM models, the abacus models, allow us to look at the stresses around openings. So we have an access opening in the bottom flange, and it's one of the things that set the minimum width of our bottom flange is make sure that we had an adequate opening to allow for inspection access. And this is obviously near the support. Even looking at the stresses around the copes, and this is just under localized load. So this is wheel load near to maximize bearing reactions and shear demands. We are seeing very, very low stresses, whether it's in the web, we'll call it the flat part of the web, or the bend radius part of the web, as we're seeing stresses, well below the mid-span stresses for a 100-foot simply supported girder bridge. From a fatigue perspective, remembering that we're only a bolted connection, that we would have a fatigue stress range of 16 KSI, and we're less than a third of that, even in the web peak under live load, under truck only. And this is not the fatigue truck. This is the full truckload. So great fatigue performance, as you might expect in these systems. And then we've even evaluated the buckling behavior of the flange arrangements. A little unusual. We looked at local buckling during concrete pouring, and very large factors of safety in terms of buckling stability. So even doing the construction evaluations in a very detailed way. Nothing surprising here, but also very robust behavior. So I'm getting close to wrapping up here. So we're approximately midway through our research program. The simple span bridge design is complete and it's out to bid. The anticipated construction schedule is on the order of summertime next year. So the follow-on work that we have to do to validate using digital image correlation to validate the behavior of these tub girder bridges and make sure our models are accurately predicting behavior will happen at that time. So we'll be out there during construction, both prior to the bridge being installed and after the bridge is installed, both prior to concreting and following concreting and then live load, so that we can get a really good sense of the behavior. The two-span bridge is currently under final design. Design is expected to be complete in about a month. And that will go out to bid shortly thereafter. And so we expect the construction also to be plates, girder sections in the field in the late summer of next year. So next year we'll be quite busy evaluating the performance of these components. And so we see a lot of promise to this, but particularly promise in terms of future work to looking at much longer spans. I think there's nothing that stops us from going to spans on the order of 250 to 300 feet using this technology. And so that will be covered in our kit of parts. Also looking at the behavior of curved girder bridges, curved boxes. And I'm even thinking that even if we were doing conventional welded tub girders, there might be an advantage to bent plate connections and corded sections, especially if we keep the cord lengths down to about 40 feet. We also see big advantages to system redundancy and internal redundancy, the value of both here. So I think it'll make sense in the future also to capture a better understanding of the redundancy of these systems and how it affects the design of diaphragms and cross frames. I can also see a reduction in the need for cross frames given this sort of structural system. So certainly we would want cross frames at any king points with corded sections, but tub girders like this have lots of inherent lateral torsional buckling capability, and particularly during erections. So there's really the potential to reduce cross frames and maybe even simplify lateral bracing. So with that, I appreciate your attention. I'd just like to acknowledge that this work is being done as part of the Joint Transportation Research Program that's under Indiana DOT and Purdue University, and the usual provisions that this represents our work and not the work of these other organizations. And then finally, just to acknowledge again, Stephanie Wagner at INDOT's been a great, not just business owner, but real partner in this. We've enjoyed our work with Indiana DOT and are looking forward to getting these bridges installed and evaluating their behavior. Same with Prince Ba. Dr. Thrall and her grad students, Sherry Ann Matoka and Marilla Tambova and Yao Wang, have been just fabulous to work with. I'd like to thank HNTB's Indianapolis office. They've really carried the load in terms of design. And then Mark Haight at Inframetals has been fabulous too to work with. And we also have taken great advantage of our advisory committee that includes Vin Bartuka, Pat Connor, Jen Hard, and others, and quite a group from Indiana DOT, as well as Jose Ortiz from Federal Highway. So we've learned quite a lot from their leadership and input, and expect to learn more over the next year or two. With that, I appreciate your attention and look forward to answering any questions you may have.